So, good evening, everybody. The Archaeological Society Malta and the Department of Classics and Archaeology are delighted to welcome you all for this, the fifth in our series of talks for 2021. I'm Patricia Camilleri, for those who don't know me, President of the Archaeological Society Malta, and I shall be mediating this evening's session. And I'd like to ask you to make sure that you mute yourselves so that we don't have any echo issues or noises off. Sometimes happens. I'd like to inform everybody that this talk is being recorded. I'm sorry if I hesitated a bit at the beginning, but I'm still admitting people who are the late comers. All this season's lectures are a collaboration between the Department of Classics and Archaeology, University of Malta, and the Archaeological Society Malta. Thanks, as always, goes to the head of department, Dr. John C. Betts, and to Professor Nicholas Vella, ASM Vice President, our link between the Society and the department. As usual, I shall proceed this evening by introducing our guest speaker, Dr. Tim Willey, then turning the virtual floor over to him. Please do ask any questions that you like using the chat at any time during the talk. And I shall ask Tim to answer at least some of those queries at the end of the lecture as time allows. This evening's lecture is entitled Open Firing, a practice-based approach to understanding prehistoric firing technologies. So let's move on. A quick word about our guest speaker. Throughout his working life, Dr. Tim Willey has been involved in the teaching of ceramics and sculpture at university and workshops in the UK and abroad. Tim studied ceramics as an undergraduate with a particular interest in experimental archaeology. This was followed by full-time lecturing in ceramics and ceramic chemistry. After completing a master's degree in sculpture, Tim spent several years researching the relationship between ecological systems and historical construction techniques, for which he was awarded a doctorate. He has established his own practice in England with a workshop in the Norfolk countryside, where he manages 12 acres of mixed woodland. This provides him with a perfect working environment and, of course, plenty of fuel for his open firings. Tim teaches ceramic sculpture and ceramic science in Norwich and is a visiting university lecturer. He is an active researcher in adaptive construction, open-fired ceramics, and experimental archaeology, and runs regular practical workshops. So now I give the floor to you, Tim.
Thank you, Patricia. Thanks, that's very kind. Hello, I'm Tim, and first of all, I'd like to thank the Archaeological Society of Malta for inviting me to present this lecture on open firing. It's a great privilege. Thank you. And thanks for organising it, Patricia. So I'm going to make a start now. I'm sure everyone can see my full screen. I've got a little bit of interference from somebody's.
Perhaps if there's somebody who's not muted, please mute.
Is that better? Yeah, that's good. So my first introductory image is of a typical open firing, and we'll be revisiting different types of firing as the presentation progresses. But as by way of introduction, I'd have to say that undoubtedly the earliest ceramics were open fired. And by that I mean fired without the aid of a heat retaining structure. Now, for the archaeologists, this can be slightly problematic in that there's very little archaeological evidence of prehistoric open firings, as the practice was very transitory and left very little trace. There's no structure left behind with open firing. There might be traces of carbon which can be attributed to all sorts of other things. So it's a very interesting and open field for the experimental archaeologist to try and unpack some of the issues surrounding it. So I hope in this illustration to illustrate that experimental archaeology can shed light on open firing technologies and answer some of the more problematic questions. And I might start with those problematic questions because they're very important. One is, and all those that have tried open firing will probably agree with me, one is, how can pots possibly survive the dramatic temperature rise of an open firing? This is problem number one. What sort of fuels might have been used? And how were open firings constructed? These are some of the important questions that I hope I might just tease upon during this presentation. But most importantly, I would consider that I'd like to illustrate how open firings involve a high level of sophistication, a sophisticated technology, a high level of material understanding, and an incredible level of organization. I think perhaps we think of open firing, or certainly I did, as very simply just a bonfire and you throw some pots on the bonfire and hope for the best. Well, over 30, 40 years now, I've discovered that simply isn't the case. I'm going to go on to the next slide. That didn't work. So I mentioned before that open firing, the simplest definition we can give is that it's firing without the aid of any heat retaining structure. Heat retaining structures are usually called kilns, but not necessarily the type of kilns that we see in modern ceramic practice. Now, since my early days with the experimental firings, way back I was a member of the experimental firing group as an undergraduate based at Leicester University. And ever since then, I've acknowledged that actually open firing is very problematic. And most experiments that particularly as a student that I undertook, had marginal successes, but a lot of failures. And you'll see why those failures occurred in a second. So these are some lovely Neolithic pottery vessels from the Kitsos cave in Greece, which was a well-known shelter where they found lots of artifacts. These have been attributed to the Neolithic, but these show quite clearly that I must add that they have been rebuilt, reconstructed. As you can see, there's only a few fragments of the original fabric, but even so, you can see from the surface of the fabric that they were almost certainly open fired. There's a lot of carbonization, which we'll talk about later, on the surface, and you can see where pots have had a sort of rough and tumble existence in the open firing. Going on to the next slide. So we'll come back to this a little later as well, this image. But this is a typical open firing schematic showing pots raised on a bed of fuel and then surrounded by fuel. As I said, we'll come back to this later, but it's important to understand that these are the essential elements of open firing. clay vessels and fuel, and that's it. So we will start with fuel because that's probably the most important material next to the clay fabric itself. And it's probably obvious to us all that the most important fuel is wood or woody materials. But there are huge distinctions between fuels. So here you can see a typical, this is my wood stack actually. This is a typical wood stack of timber which has been felled and cleaved into sections, which has been technologically possible for millennia. And over on my left, you can see what we would call branch wood or brushwood. And there's a very important distinction between the two because they behave in very different ways. For instance, cleaved wood, which we normally call timber, has a slower firing cycle than thinner branch wood or brush, as we'll probably call it. Brush gives off heat very quickly and it dies down very quickly. Timber has a capacity to keep the fire running for longer. So I found that the fuel type is incredibly important, and a mixture of fuels is often the way forward in terms of open firing. Now, this is collecting reed from my. I'm very lucky to have a reed bed close by. Well, just over the road, actually, just out of the window behind me, and I can collect reed. It's part of Norfolk Wildlife Trust's reed bed, and reed I found to be a very useful material in open firing. Reed contains, and grassy materials such as reed, have a high silica content. And the high silica content really aids the radiation of heat to the pottery vessels, which we'll see later on. So again, this is a very important fuel along with timber and brush. I should say now that probably the most important thing related to those materials is that they have to be completely dry. I've witnessed and been part of open firings where the wood hasn't been completely dry. And a huge amount of energy, I can't stress this enough really, a huge amount of energy is simply wasted in converting the moisture content of wood, which can be anything from 0 all the way up to 50%. So if your wood or your fuel or your reed is moist, you'll spend all the energy from the flame will be converting that moisture to steam and not going into the pots. So dryness is really important. So open firing can be quite seasonal. For instance, today it's a really damp day here in Norfolk, and I wouldn't have a chance of getting the fuel completely dry. And if it was dry, as soon as I construct the open firing, the moist atmosphere would create inappropriate conditions. So I call the construction types of open firing as the architecture, because that's really what it is. There's lots of different types of lots of different forms of open firing architecture. And here's just two of them, two which are very important to me actually. This is like what you'd probably call a typical bonfire firing. And you can see here, there's bundles of the grassy material, which in this case is reed. And here we've got branch wood. Now over here, we've got an interesting structure which I call a firing stack. Now, because there's very little archaeological evidence of how these open firings were constructed, doesn't mean that we can't make very informed decisions on how they were structured, because in certain world cultures, they still open fire. And perhaps the most important location for open firing is Papua New Guinea. And in Papua New Guinea, they still open fire pretty much, one supposes, as they have done since way back in the Neolithic period. And it's an incredible place because it's an unbroken tradition. In the 80s, Margaret Tuxon and Patricia May undertook some really important research with Papua New Guinean ceramics, and which was published in a book called "The Traditional Ceramics of Traditional Pottery, of Papua New Guinea." And in there were really interesting descriptions of mostly how the pots were constructed, but also to a lesser level, the different kinds of kilns they were using. And I did notice in a tiny little image in the book that was published, and it was only the edge, I have to say, of what I call now a firing stack. And we'll see some more images of this firing stack. And what was interesting is that they used this timber. They didn't use newspaper, I hasten to add. I've used newspaper and leaves as the fuel, and they would set the kiln stack alight and then place a single pot into the stack, almost at full temperature. It would fire within 10 minutes or so, and the pot would survive, which I thought was incredible. Because if you think of modern ceramics, you'd take 24 hours to fire a pot, so it would survive. These were firing in 15 minutes. Now, a little look at the clay bodies. We'll be coming back to firing later on, by the way. So in terms of clay, a lot of our decision making in replicating or hypothesizing on what clays are used for open firing are based on sections such as these. We can look at sections of ceramic fabric, and we can see that if I look at here, we can see that there's clay surrounding particles of, in this case, it's sand. I don't know whether you can see, but the particles are rounded, which is typical of a river, probably a river sand, could be a marine sand. They've been rounded, but they've been moved by water. And if we look at this section here, we can see that they're much sharper. And this is ground up ceramic, commonly called grog. So wasters from ceramic firings would be crushed up and used as well as the clay within the clay body. So a clay body is not just clay as you would find in the ground. It's a mixture of clay and temper. So the temper can be a number of things. This is sand, this is grog, and I'll move on to the next slide. And here we've got a powdered clay collected from a geological site. And this is what we call grog, which is, as I say, a ground up ceramic. So from those clay body sections, very often the experimental archaeologist has assumed, well, it's basically clay plus tempering equals a suitable fabric for open firing. But even so, invariably this happens. When you fire at those rapid temperatures, and we're talking about ambient temperature 20 degrees to 800, 900 degrees centigrade in such a short time frame, this happens, and this is called spalling. And it's the bugbear of open-fired potters, I'm afraid. And what this is that no matter how dry you think a clay's fabric, the clay pot is, it still contains significant amount of moisture. You can dry it for a long period, but as soon as it's away from the heat, it will start to absorb, the clay body will start to absorb moisture from the air. The clay particles are extremely fine in the clay itself. I'm not talking about the opening material that you can see in little specks, but the clay itself, incredibly fine particles so it's got a huge surface area. And that surface area is negatively charged as well. Clay minerals are negatively charged, and they attract the dipole water molecule very quickly. So it can be a matter of minutes while you think you have a very dry pot from a very dry atmosphere, putting it in a bonfire. Within those few minutes, it can start to absorb a lot of moisture. Moisture converts to steam, and in terms of volume, it's 1,600 times its volume. So from a small amount of moisture, you then suddenly, at 100 degrees centigrade, have 1,600 times the volume of steam. And that's what's happened here. So this has been fired in an open firing. It's simply clay plus tempering. And the tempering material, these little specks here, that's grog. And it's nearly 50% grog. So just adding grog, we'll call it tempering, to clay is not the whole picture. It's still problematic, and it would have been a problem for potters for thousands of years, which they solved. So in a number of trialing a number of clays over the years, I want to just tell you a little story about a clay which I call not very glamorously T14. It's called T14 because it was the 14th test of a clay which is found at a location called Trimmingham, again in Norfolk. This is the site. This is actually this is the beach. The sea's behind, and this is a glacial till. So it was shifted by glaciers, and it's been deposited as this along this cliff face here. And there's a lot of really interesting material here. This area here is very clay-like. This is more silty, and this is sand. And if we look over here, this is the clay. So the clay is full of these limestone nodules. That's not necessarily a problem because we can get rid of those limestone nodules. But this T14 clay has some incredible properties. And I think that it's those properties of this particular clay that was key to the success of open firing historically. It's key, and it was probably key to the success of the firing in places like Papua New Guinea, and no doubt for thousands of years, potters have known that you have to get exactly the right type of clay. I'll move on to the next slide. This is the Trimmingham till. That's just to show the different sorts of deposits That's the clay there. There's a little nodule of limestone. That's what I used. This is a silty material and 2 types of sand. But it was just this clay which I found to be so successful, T14. Incidentally, T14 is no longer there because it's been washed away by a storm. So it's no doubt I'll find something similar. But it was interesting that after sieving, there's T14 again, and I've sieved all these nodules out. These are limestone nodules, which are incredibly problematic with firing, which you'll see later. And then the sieved clay as a slip is dried out. This is plaster, and this is the clay drying out. And here you can see that it's formed a nice plastic clay. So it's been sieved. It's still got, if you can see here, it's still got tiny specks of limestone. But you can see it's very plastic. This is another test, not T14. And you can see that this one actually started to crack when I've bent it. So this one isn't as workable as this one. So to that clay, I wanted to add tempering. And just a quick introduction to tempering. Tempering, as we discussed earlier, is a coarse ground material. It's inert. It hasn't got any clay mineral in. As such, it's used to what they call as an opening material. And it does stop a lot of disruption in terms of cracking and spalling, but not, as you saw earlier, not totally. It's part of the solution, but it's not all the solution. So these are, if you look at clay fabric from prehistory, you'll see that a lot of ceramics has got this. This is mussel shell tempering. You see a lot of shell tempering in archaeological examples. Now, I mentioned earlier, this is just to illustrate, that shell tempering is calcium carbonate, shell being calcium carbonate. But calcium carbonate, after firing, turns to lime. And lime, when it's after firing, when it's exposed to the atmosphere, rehydrates and forms these little nodules which pop the clay out. This is typical spit out caused by small amounts of limestone still in the clay, which have been converted to lime in the kiln. So it's a wonder why limestone was used and why shells were used if it causes this problem. And that's ongoing research that I'm doing at the moment. But strangely, adding a small amount of salt or seawater subdues this effect quite drastically. And it's interesting, but the potters of Papua New Guinea also use, in many of the cases, they use seawater to mix with the clay. But that's just an interesting issue which is ongoing. Maybe I'll come back for another presentation at some time. Now this is opening material, 2 types of opening material. This one is sand, silica sand, and you can see that the grains are rounded. This one is grog, crushed up ceramic material, easily made from waste ceramic. And there's evidence of grog being used in prehistoric pottery, and there's evidence of sand being used. What you can see from this is that the rounded grains of sand and the sharp grains of the grog are very different. And I found, I'll go on to the next slide. I found that actually sand is one of the least successful types of opening material. This is oyster shell tempering. Can you see how it's beautifully interconnected and is forming a really strong lattice bond with the clay? And also this sharp angled grog is intersecting the clay and holding it together. With sand as a opening material or a tempering, those round grains don't cling on to the clay as much and don't create the same sort of structure that these sharper fragments do. And also, as a sort of side issue, really, I suppose, but silica sand, many sands are based on are silica sands. They have a what's called quartz inversion. So they actually expand and then contract at 557 degrees centigrade. And again, that can be problematic and that can cause the pot to fail. So of all the opening materials, I chose grog to do most of my experiments. Now, this is T14 with 50% grog, fired in 15 minutes. And it's a pot which I thought wouldn't, like many of the others I fired at that crazy rate temperature rise, I thought it wouldn't work. In fact, I lit the fire. I went home for a cup of tea, thinking I'll just go back to another broken pot. And there it was, completely intact. And I thought, my goodness, what is in T14, that clay, that protects it from spalling or cracking or blowing up? Going back to the other, there's identical, two test pots, identical size, identical firings. This one is in just a natural clay with 50% grog. This one is the T14 clay, again, 50% grog. And you can see what one blew up and the other didn't. So this concept that's really, I've been working on, since a student, the concept that all open firing clays are just a mixture of, you found clay and a lot of tempering, isn't the whole solution to stopping spalling and cracking and huge losses. It's got to be something in the clay itself. So I decided to find out what that was. By process of livigation, which is just settling out the liquid clay in a plastic drinks bottle. Not very scientific, but there's a microscope next to it to show that it is scientific. So you have, after settling out for about 24 hours, you have plenty of water, a sample of clay, give it a good shake, let it settle, and you can see you've got the water there. The next layer to settle out is the clay mineral, which is incredibly fine. And at the bottom, there was this layer. So this is the successful T14. After drying out, you can see that the clay minerals, which I dried them out separately, I separated each layer. The clay mineral was about 53% by weight. The silt was 47% by weight. And the grog, which I added later to the clay, was 50% of the total. But it was this relationship which was my sort of eureka moment, I guess, because it had an incredible amount of silt, which is actually non-plastic. It doesn't, this is the clay, this is what we call clay, which is a clay mineral. Illite, montmorillonite, kaolinite, these are the clay minerals that give plasticity, workability. But it's had a huge amount of this non-clay, very fine material in the form of silt. And I hypothesized that it was the silt that was giving the integrity to the structure of the fabric and was very resistant to spalling. rather bizarre diagram I've done there, but this might illustrate the mechanism at work here. So, and I'm very conscious of time. Time's running on, but I'm just going to try and illustrate how this works, this system works. So if we look at a clay particle, we can see the individual clay particles are by nature flat platelets. All the clays, illite, microilmenite, kaolinite, etc., are flat platelets, incredibly fine size. And as I said, they absorb water and they attract water, and the water lies between the fine particles of clay mineral. That's what causes the plasticity. If you imagine a pack of cards, or better still, sheets of glass with oil in between them, they slide about effortlessly, and that's what is creating the plastic material that we call clay. But clay by itself, the clay mineral by itself, can be over plastic, and to be workable, there's a difference between plasticity, which is the stickiness that you get with clay, and workability. Workability is how well the vessel stands up when you're fabricating it, when you're coiling it, or even throwing it. And if you imagine that this clay particle, here's a schematic of the clay particle surrounding very fine particles of non-plastic material. Well, these clay particles would coat these small non-plastic particles, and they wouldn't diminish it wouldn't diminish the plasticity that much. In fact, it might aid the workability of it. And here, by comparison, probably bigger than this actually, is a grog particle. So if we look at all this here, this is what's going on in T14. We've got grog, we've got clay minerals, and we've got very fine non-plastic material. This is non-plastic, these are non-plastic, the only plastics are here. But that clay is very, very workable. And therefore, within the whole matrix of the fabric, we've got comparatively small amount of clay. And by that, and by virtue of that, we've got a much less capacity to hold water. So in replicating that mechanism, I went on to synthesize the system. So to try, as a sort of control, if you like, a control to see if the system can be replicated and duplicated with consistent materials. That clay T14 is very transient. It washes out. It's on the beach. The clay strata is changing all the time. But if I could replicate that and prove this hypothesis that it was ultra-fine non-plastic particles that were the answer, I might be able to form a more cohesive argument for this. So this is what I after a lot of trials, I have to say, the true Rimal is a fairly pure clay containing mostly the clay mineral illite. Bentonite is a pure clay mineral, which is the montmorillonite. And as the silt, as a replicator of the silt, I use this very fine malachite. Malachite is a very fine powdered fired china clay. It's been fired, so it's non-plastic, but that could be any filler. I mean, we talk of it as a filler, and that was duplicating the component of the silt, and then again, as before, grog. So that's replicating in a synthesized version of the T14, and this is the grog. And that's the outcome. Again, super fast fired, 15, 16 minutes this took, and it survived. So I think that by doing this, I've got more of an understanding that it's actually not, it's not just clay and opening material that potters just mixed together and made very successful pots. They must have had an insight into clays that had these sort of properties. Now, I'm not saying that they would know that it's the superfine non-plastics that give success, but it's interesting to note that in, say, in Papua New Guinea, even though some of the settlements have got the pottery settlements in particular have got clay right next to them, they will travel by foot for miles, for days, to get particular clays from particular locations, which they know will work. And it's probably because those clays have got a high percentage of very fine non-plastic materials as part and parcel of the material. So this is my baseline formulation. It's now called SY14, so it's a synthesized T14. So I've got by batch a Truriamal, which is a red clay from Staffordshire, pottery centre of England. Bentonite, which is a pure Montmorillonite clay, only 5% of that. 200 Malachite, very fine. That 200S means that's the mesh size. The 200 mesh is a very fine sieve, so it'll pass through a very fine sieve, and that's about the same as I found the silt was, and that's 25%, and then as before 50% grog. So with this synthesized version, I've had success after success, really, with very rapid firings without the need to preheat. So fine grain non-plastics, that's the key. I hypothesized, but that is the key. It increases workability by giving strength and malleability to the clay. It reduces the need for a high clay mineral content. So the proportion of tempering is greatly increased. So if you remember that diagram, by adding these fine non-plastics, the actual clay actually by proportion decreases. And by increasing the proportion of tempering, greatly increase the porosity of the body, so allowing gases to escape. And the fine particles also bridge the differential bit of the system from the coarse grains of the temper to the ultrafine clay particles, and so increase workability and mechanical strength. So in a nutshell, I guess it's important to understand that what we think of as clay is far more than the pure clay mineral. It actually is clay mineral plus other fine materials. And it's finding that in the wild, that correct balance, which I'm sure potters of prehistory would have knowledge and a deep understanding, not of the technology behind it, but of the need to find those sort of clays. Quickly to finish off, I'm just going to show a few types of firing. This is again a typical open fire. This I've used just old sheet material to replicate the timber. You can see the timber stack I've got in the back there. So that's a typical open firing, bonfire firing. And this here is, which will come back a little later, if we've got time. Yes, we've got time. Is just to find out why reed materials or grass materials are so good at radiating heat. I said we come back to this image. So for open firing, once we've got the clay body sorted out and we found a clay body that can withstand this super fast firing, we've got to maintain temperature. We've got to get to around, well, from anything from 750 to 900 is normal in terms of centigrade to turn a pot into a strong fabric. And it's no use having the pots on the ground. You've got to get, because once they start to lie on the ground and invariably into ash, ash is an incredible insulator. So the heat cannot get at them. So it's best to have them raised up off the ground with fuel underneath. So it's common to have, well, it's beneficial I found, to have fuel underneath and then fuel around the vessels themselves. Here's two typical open firings, and you can see the extreme. I mean, you can imagine, can't you? Well, I hope from this you can see how rapid the firing is. I mean, it's frightening. You know, with super dry materials, you light the fire, within 10 minutes it's at top temperature, within 15 minutes it's all done. And this is, again, one of found properties is one of the best types of open firing for, of this traditional sort anyway, is to have fine reed-like material inside the kiln, inside the structure, and then branch wood on the outside. The grass-like material really radiates heat and it glows like the bars of an electric fire and pushes and radiates heat into the pots. Now, this is not traditional, but these clays are what just standard clay plus grog, and which under normal circumstances would blow up in those super fast open firings. So to test different clays, I made this firing grate where you could preheat the pots slowly, maybe taking hours, preheat them, then put fuel on them, and then fire those successfully. So this is not replicating a prehistoric firing in the slightest, but it does show another angle to fire pots. Some clays you just will not stand the extreme temperature rise. So it's not uncommon in parts of Nigeria, for instance, it's not uncommon for potters to still preheat the pots on a separate hearth and then fire them very quickly before they take on moisture, quickly then fire them. And this is this is what I call a firing hearth, and it's enabled me to do lots of tests with different types of clay and see how they withstand open firing. And here you can see the open fire, they're being preheated, fuel on top, and then these are the fired pots. This shows, I hope, again, this is just an experiment. This is stainless steel mesh, which is not a Neolithic technology, but it's just to show this that the heat, the incredible intense radiated heat of very dry, grassy materials. It could be reed, it could be grasses, but they are high in silica. And you can see the pot, there's a single pot in there. And this is glowing red, and you can see the pot glowing red. We know that that's going to be in the region of probably 750, 800 degrees there. So it's gone to the high enough temperature to turn it into viable ceramics. And here is my favorite kiln. This is the firing stack, which is my best guess at what the Papua New Guinea stack would look like. So there's just a stack of very, very dry wood. The wood is less than 10% moisture content, which is very dry. Stack, light a fire, and there's wood and leaves in the center as well. Light it. The stack is like a vented stack, as you can see. So it lets lots of air in very quickly, and it really does go very quick, very violently. And then the pot is literally thrown into the top, but when it's really when the fire is really raging. And there you see the stacks burnt, the stacks collapsed. The collapsing of an open firing is very important, because as it collapses, you want the collapsed burning embers to get close to the pot, lock out any drafts that will cool the pot, and radiate heat into it. I found that it's this, if I can show you, it's this radiation and conduction in this case, because there's red hot embers in the pot that fire the pot. It's not the flames. Flames do actually very little in effect, and I found it's the embers and the glowing embers, and particularly those glowing reeds, which we showed earlier. And there's a pot. It's got a lovely ring to it, and it's completely spore free, and again fired in just 15 minutes. So to conclude, I think I'm just about on time. To conclude, here's just a few pieces that have come out of the kiln. Some of them you've actually seen in the photographs earlier. This one, I think I think that was one I was just doing. This one is a decorated pot. You can see that it's a very coarse fabric, and it's been fired in that was fired in a stack, and this is just slip decoration, white clay decoration. This one here shows the different effects one can get in an open firing. This is heavily impregnated with carbon. If the open firing, excuse me, is choked with fuel, and you allow little oxygen in, particularly at the end of the firing, you can turn your pots black. This was undoubtedly done in the past, because there are lots of evidence of black pots. And the way you do it, you have an open firing, get the oxygen in, get the embers falling on, and getting the pot up to temperature, but then you can choke the firing once it's fired with and it can be damp material with leaves or grasses, and then you can choke it up, and it will be an incredibly smoky firing, and that will impregnate the pores of the pot and make it go this lovely black color. Here's another two pieces fired in an open setting. Again, you can see how black that was, deliberately blackened. And another one here, which is interesting because you can manage by various means. If the bottom is submerged in ash, you can then just throw organic material over the top to make just a top black. And finally, another two. Again, this is fired and was completely bright terracotta color, and then I put more fuel on and carbonized it. And this is an interesting one. That's typical, isn't it? The beautiful sort of colors and textures the open firing gives you. You've got this carbonization area, and you can see where the flames have cleaned this surface up by just burning the carbon back off the surface. And you can see that the pots change in the open firing. That's a wonderful thing about open firing, because you can watch things happen, and they can be suddenly all very black, and then a flame will suddenly rekindle, and it will flash, and it will brighten up the whole surface. It will just burn the carbon away. And that is it. Thank you very much. I hope my mic was on.
Yes, I think it was. I just managed to put mine on now. Well, thank you so much, Tim. That was, full of amazing information, and your passion for your subject obviously comes through really clearly when you talk about these lovely things. The examples you've just shown us were absolutely divine, beautiful designs, apart from anything else. I know there are some questions on the chat. I do hope we've got some interesting questions about perhaps the general themes of what you've been speaking about. Just before I start with the questions, I was always thinking, obviously, of trying to make some sort of a comparison with how things might have been done in Neolithic prehistoric Malta. And I was thinking of the fact, one of the practical facts about drying, the possibilities of drying. I think in Malta, drying things out very well is probably a much easier task than it would have been, that it would be for in an English, in a wetter context, shall we say.
Yeah.
So I was also interested in the materials that you spoke about, the reeds and the wood, which even for our Neolithic Maltese would have been probably not available. And it would be interesting to see what differences there might be, between the kind of materials they would have actually had access to at the time, the burning materials, and the kind of burning materials that you have been using, and to see what comparisons could be made about that, and your experimental measures, your methods would be extremely useful to getting to the bottom of that.
Yeah.
I'll just go back to the questions in the chat.
Okay.
I don't know whether you can see them yourself. Emma, hello. Which technique did you use to separate the two fractions, silt and clay, after levigation?
Oh, that's a good question. Because I used a plastic bottle, what you do is you let it settle in the plastic bottle, you see the different sediments, and then you take the top sediment out, and the way you do that is with a red hot needle, you puncture just underneath in the plastic bottle, just underneath the water layer, and that will spurt out. So you can get rid of that, if you're following me. And then you can do the same with the silt and the clay mineral. You just puncture it underneath. So the water's gone there. You'd put a second puncture hole in the bottle underneath the clay layer, and that will spurt out, and you can collect that as liquid clay, slip, and then you're left in the bottom of the plastic bottle, the silt. So you do it by squirting it out. And then, of course, you recycle the bottle.
Of course. Another question. Good evening. Through my research and also through my personal experience as a sculptural ceramist, I find that I get next to zero casualties in my firings. I have put it down to the thickness of the fabric. Eastern and African potters who open fire also do have rather thin walls to their pieces. Do you think this would help? Being thin, they hide less water, dry faster, and also pre-warm faster.
Yeah, well, there's two issues here, really. Yes, having a thin wall will allow the moisture to or the gases to escape much easier. The thicker a ceramic piece is, the more likely it is to blow up, and that's true with modern ceramics. That's why a brick kiln will take days to reach temperature, because otherwise the bricks would just blow up. Whereas very thin walled pieces do allow moisture to escape. The thing about thin walled ceramics in an open firing setting is that you have to have them arranged so that there's no drastic collapse, because they break very easily. But you're absolutely right. A thinner wall section is much better. And some of the African examples, which were coiled and then a handle, usually a anvil and paddle technique, are incredibly thin, and that would definitely help. And for all the reasons you say, really, they hold less water, they dry faster, and they would pre-warm faster. But again, looking at the range of open-fired ceramics, it does range from very thin to quite chunky. But you're right. But that is an important point, the thickness.
Just association of ideas. I was just thinking of coiled pots. Does the method actually of creating the pot itself have any effect on the ability to, I don't know, survive better in the, or less so, in the open kiln, open fired situation?
Yeah, well, the coiling techniques vary dramatically, and I think that the traditional coil technique that we think about of putting, like, rolling one or laying one coil on top of the other actually isn't the technique that's prevalent in a lot of coil building pottery cultures. The way they use coils is they overlap the coils on the outside and compress them together. So it's actually, the process of coiling actually is just to get the clay in position. It's not a construction technique. What they do, they put it in position, but either on the inside or sometimes on the outside of the last coil, and they squeeze the two together. And that squeezing is the actual building. The coiling is getting the clay there, and it's the squeezing together. Because you're right, you need that strength. If you just lay one coil on top of the other with a bit of slip or something, that's not a particularly strong way of hand building.
Anne is asking, ever practical, how come you stack your timber in the open air? Can it ever dry?
Where's that? Oh yes, I've got that. Yeah. The timber you saw in the stack, that dries out in the open for the summer, and it doesn't. And if it rains on it, that's absolutely fine. Actually, rain is not so wetting as a damp atmosphere, strangely enough, because as soon as the wind blows over it, that stack is open to the wind. That's very important. And the end grain is exposed to the wind. That's really important, because wood loses about 80 times more moisture from its end grain than it does radially. So that's really important to have the end, and it acts like a wick because the fibers are going that direction. And if the wind is blowing against the surface of that wick, it sucks the water out. But then in the winter, I cover it up. And then for firings, I would take some of that wood and I would put it into an even warmer, drier environment for a week or two before the firing. But a very good question.
I noticed that the next question was anticipated my one about the coils. I think you've explained, given us an explanation for that. You mentioned at the beginning of your presentation something about limestone. Now, of course, Malta is limestone, so I wonder whether that could be seen as a disadvantage or as an advantage. What do you think about limestone as, I don't know, grog or?
Yeah, limestone is problematic only in that it's ideal actually as an opening material, absolutely ideal, except for the one thing that it causes. They call it lime pop out or lime spit out, where the limestone calcium carbonate converts to lime, and then it hydrates after firing. It's lime, and then it rehydrates in the moist atmosphere, and then expands and pops. But the work that I'm doing now, the work that I'm doing now, I'm getting some interference there. That's it. Can you hear me now? Mm-hmm. Yeah. So the work I'm looking at now is why are calcium carbonate materials so prevalent in the fabric of Neolithic, Mesolithic pottery? And one of the things I've tried is just using seawater, and it actually works. Seawater stops this phenomenon happening. Whether the salt and the limestone are creating calcium chloride plus sodium bicarbonate as a sort of an equation. And so negating, you know, so bypassing, but I'm not a chemist, and that's just a high, you know, just a guess, best guess really, but something's happening there. And there's a reason why the potters of, for instance, Papua New Guinea use salt water. So it's a best guess. There's not much research on that, but it's a fact that it does exist and it does work.
Well, there's plenty of seawater in Malta, that's for sure. So no problem there. Well, I'm not seeing any more questions on the chat, so I think we can bring the evening to a close. Certainly, we hope to see you in Malta, Tim, one day.
That'd be nice. That would be nice.
So we can have further discussions on.
There's another question. That quick question.
Is there another one I missed?
What making techniques do you use, please, Tim? Are they all hand-built coil pots? Yes, they are. They're hand-built with a coiling technique, which I just described, which is squeezing them together, so they're sort of coiled and pinched.
Yes, well, lots of thank yous from everybody, including Nadia, who asked that question.
Oh, thank you.
Well, I mean, it just remains to thank you all. We had quite a nice group today on board. Thank you all so very much for participating in this evening's event. We look forward to seeing you again on Wednesday, 20th April for Borgin Nadur, 100 years on, a presentation by Katia Stroud, Senior Curator Prehistoric Sites at Heritage Malta, and Dr. Joseph Caruana, Curator Prehistoric Sites as well at Heritage Malta, for our next lecture. Just a reminder that recordings of many of our lectures can be found on our website or on our dedicated YouTube channel. As always, I urge you all, those who are not members, to become members of the Archaeological Society Malta through our website at www.archsoc.org.mt. In that way, you will be supporting the Society in its lecture programs, its peer-reviewed journal, the Malta Archaeological Review, which is online on our website, and also in its advocacy work in support of all things archaeological in Malta. Sincere thanks from the Archaeological Society Malta and the Department of Classics and Archaeology at the University of Malta to Dr. Tim Willey for his most interesting and informative talk this evening. Do follow us on Facebook and on our website, and thank you so much, and good night.